Hi everyone, welcome back. Welcome to another episode of fun-filled calculus material. Today we're going to be talking about related rates. And when we're talking about related rates, what we are looking at is not only these application problems for derivatives, but we're also going to be looking to see how we can relate some of these variables or how we can relate some of these changing rates to one another. And therefore we get the namesake related rates. Now on screen here at the top, you're going to see this problem solving strategy for related rates. And what I want you to do is I want you to focus on the very first process here, or the number one strategy, that says that we first need to draw a picture and then we're going to name the variables and constants. Once we do that, we're going to use t for time, and we're going to assume that all variables are differentiable functions of t. So that is the one most important key that we're going to be focusing on as we work through these particular problems. Yes, we're going to want to make sure we have an equation that relates the variables, but as you'll see, those equations will either come from geometry or from trigonometry, and we'll be able to extract them given the picture of the problem, which again, number one, encourages us to do so. So let's go ahead without further ado and let's jump into the very first example. In this very first example, we have that the length of a rectangle is increasing at a rate of 8 centimeters per second, and its width is increasing at a rate of 3 centimeters per second. When the length is 20 centimeters and the width is 10 centimeters, how fast is the area of the rectangle increasing? Okay, so we are given a lot of information here. Now, again, what I want to do is I want to draw a picture really quick. And once I start drawing this picture, then I want to go ahead and I want to start extracting a little bit more in the sense of what variables will I be needing. So it says that I have a rectangle. And so that's going to be one of the first things that I draw. This rectangle. Okay, so I have a length and I have a width. All right, so that's what I want to start off with. And I want to start off by identifying that. So I have some sort of length. Okay, so I'm just going to call my length L. And I have some sort of width as well. And you guessed it, I'm just going to call it W. And so what they're telling me here is that the length and the width are both increasing. So this width is increasing and this length is also increasing. Now remember, when we assign these variables, we're going to assign these variables, and like step number one says, we're going to think of these variables, or we're going to assume that these variables are differentiable functions of t. So when we're looking at the information that is given to us, it says that the length of a rectangle is increasing at a rate of 8 centimeters per second. Okay, so my length here, this length is increasing at a rate of 8 centimeters per second. So what I'm going to do is I'm going to outline that. I'm going to say that my change in length, or my rate of change for the length with respect to time, is going to be 8 centimeters per second. Similarly, we're going to be able to extract that the change in width with respect to time, that is given to us, that is a rate that is increasing at a rate of 3 centimeters per second. And so this is where that whole process for problem number 1 came in, to say that we want to draw a picture. Once we draw a picture, we can then extract what variables we're working with. Once we extract those variables, we're going to assume that the variables are changing with respect to time. Therefore, the change in length with respect to time is 8 centimeters per second. The change in the width with respect to time is going to be 3 centimeters per second. And that's really all that we want at this point in time. All right, so again, oops, I didn't want that color. I wanted green. There we go. So this was one of my rates, and this was my other rate. One was for my length and one was for my width. Now, the rest of the information that is given to us. When the length is 20 centimeters and the width is 10 centimeters, how fast is the area of the rectangle increasing? Okay, so we had a little bit more work to do there, but it's okay. When we're looking at related rates, what we're essentially doing is we're observing these variables change. And when we're observing these variables change, what we're going to do is we're going to stop them at one point in time. In other words, we're going to observe a cross-section of time, and we're going to be able to extract how fast a certain quantity is then changing with respect to time. Now, because it's going to be a cross-section, it's going to involve a lot of variables moving. And so again, that's what we have to account for. And to tie this in, what we're going to be looking at here for that second sentence says that the length is 20 centimeters and the width is 10 centimeters. That's a cross-section. In other words, that is going to be the piece that I want to focus on. We know that they're changing, but when they're changing, when we get to 20 centimeters and when we get to 10 centimeters, we want to know how fast is the area of the rectangle increasing. So I'm going to put these down, that my length is going to be 20 centimeters and my width is going to be 10 centimeters. Okay, so again, the length, it's not starting out at 20, but it's starting out at some other value. And we know that the length is increasing, and it's going to keep on increasing. We just want to know that when it's 20 centimeters, what is the rate of change for the area? Well, we now need an equation that is going to govern all of these variables that we've now defined. We've defined W and we've defined L. Naturally, the area of a rectangle here is area is equal to length times width. That's really great for us. And what I'm going to do now is, once I found this equation that relates the variables to the object in question, what I'm going to do is I'm going to take the derivative with respect to time, because I want this area to change, or as I'm observing this area, it's changing with respect to time. So on the left hand side, we get that we're going to be calculating the area, the change in the area with respect to time. On the right hand side, we know that the length and the width are both individual functions that depend on time. Therefore, we have to use the product rule. And so here I'm just going to say that we're going to use the product rule. So the product rule is then going to say that we have to take the derivative of the first function. So derivative of the first function with respect to time multiplied by the second function, which is width, plus the first function multiplied by the derivative of the second function. And there's our product rule. Now, the nice part about this is that we have already extracted these values. We know what everything in this equation is because of the prompt that was given to us. The change in area with respect to time, well, what was the change in length with respect to time? That was your 8 centimeters per second. What is the width at that specific time? That is going to be 10 centimeters plus the length at that specific value, it's 20 centimeters. And finally, the change in width with respect to time, that was your 3 centimeters per second. In other words, we have everything that we need. All we're going to go do now is distribute and combine like terms. 8 times 10, this is going to be 80. Carry your units of measurement, centimeters squared per second, plus 60 centimeters squared per second. Add those two together, and we get a really nice answer of 140 centimeters squared per second. Now, that stands to reason that this would be the change in the area with respect to time because it carries the same units of measurement. The area is a quantity squared, so that's going to be a square centimeter per time, in this case, seconds. So to summarize this, here goes my summary. The area of the rectangle is increasing at a rate of 140 square centimeters per second when the length is 20 centimeters and the width is 10 centimeters. And this is the type of answer that I want to see on an exam right here, what I am boxing. I want to make sure that the answer that is displayed is a verbal representation of the work that you found. Now, because of the drawing that we had and the prompt of the problem, we were actually looking for an area that was increasing. In other words, we were looking for a positive rate of change. However, if one of the values was one of the sides was, let's say, decreasing, then we would change one of our rates to be decreasing, meaning one of the rates would be negative. So anytime that we're given that the rates are increasing, we are talking about positive rates. If anytime we get a decreasing rate, then we must interpret it as a negative rate of change. Awesome. Let's work with the next problem. Here we have this example that says, at noon, Ship A is 150 kilometers west of Ship B. Ship A is sailing east at 35 kilometers per hour, and Ship B is sailing north at 25 kilometers per hour. The question now is, how fast is the distance between the ships changing at 4 p.m.? Ooh, okay. So we got some work here. The first thing that I'm going to do is I'm going to draw a picture. Okay, and they're giving me a timestamp. They're saying, hey, at noon, this is what we're observing. So at noon, Ship A is 150 kilometers west of Ship B. Okay, I'm going to keep that in mind. Ship A is sailing east. Okay, so I know that Ship A is going to be sailing eastward, and Ship B is going to be sailing north, okay, at 25 kilometers per hour. Awesome. So let's go ahead and let's start with that picture. All right, so I have ship A. Here goes ship A. I put a little boat that looks like a bathtub. There it is. So this is ship A. And this says that ship A is 150 kilometers west of ship B. Okay, so I have ship B then somewhere over here. Because if I'm looking at a compass, then I have north, east, south, and west. And therefore, by my drawing, ship A is to the west of ship B. Okay, and they're telling me that it's 150 kilometers. So I know that the distance between the two is 150 kilometers. Perfect. Now ship A is sailing east. Okay, so ship A, you're sailing east. So ship A is going to be moving in the direction to the right. And ship A is going to be sailing at 35 kilometers per hour. So 35 kilometers per hour. Awesome. Ship B is going to be sailing north. All right, so ship B, you're going to be sailing north. Moving upward that way. Perfect. And you're going to be sailing at a rate of 25 kilometers per hour. Okay, so how fast is the distance between the ships changing? All right, so again, what I want to look at here is I want to start assigning some values or some variables, and then we're going to go through the whole process of relating the variables to an equation, and then we'll go ahead and we'll take that derivative. So let's not put the cart before the horse. Let's go ahead and let's focus on what we have. So notice I don't really have variables here. I do have an identification for ship A, and I have another identification for ship B. But again, there is no variable here. So what I want to do is I kind of want to get some variables in the mix here. All right. So what I'm going to do is I'm going to start by enhancing this picture for this picture to be moved just a little bit more. Okay. So, oh, and I forgot one more thing. By the way, this was happening at noon. So all of this is at 12 p.m. I'm going to fast forward to 4 p.m. All right, so let's fast forward to 4 p.m. Okay, so 4 hours has now passed. Now, what is the distance for ship A? Or let's say, what is the location of ship A? Here's the thing for this. Ship A now has traveled a certain amount. Well, let's go ahead and let's figure out that amount. Ship A was sailing east at 35 kilometers per hour, which means that when ship A when we want to find this distance for ship A, we need a rate and time. The distance we don't know, but the rate we do know. That was at 35 kilometers per hour. Multiplied by the time, which was the 4-hour time difference. So all we have to do is take 35 and multiply it by 4. And we get 140. Which means ship A has traveled 140 kilometers so far. So 140 kilometers, that's how much it's traveled so far. Okay. So again, we're going to keep that in mind. That way we can show this picture in a little bit. I want ship B. So let's go to ship B. Ship B, do the same process. Take the same approach. Ship B was moving at a rate of 25 kilometers per hour for 4 hours. Well, this one's kind of nice. 25 by 4 should get us 100 kilometers. So now comes my picture. I have ship A and ship B move now 100 kilometers upward. So ship B moved 100 kilometers upward, or to the north. So ship B is somewhere over here. There we go. The distance between them is the distance that we want to find. Now, as you can see here, we have this right triangle. Well, we know ship B moved a total of 100 kilometers, so that whole distance that it traveled from its original point of observation was 100 kilometers. Ship A traveled a total distance of 140, but the initial distance was 150. So the big question is, how much distance is left over? That distance that's left over is 10 kilometers. So ship A is only 10 kilometers away from the initial point of observation from where ship B was. And now we have a distance. So here's a distance that we get to look at. So how fast is the distance between the ships changing? That's what we want to find. All right, so we're gonna kind of keep that in mind. Okay, we could label this distance lowercase d if you'd like, and that would be fine. However, I also want to look at some different observations because I also need a variable. Notice the way I drew the picture, we have a right triangle where we would naturally get some x value, some x component, and some y component. If I label my x component as a horizontal change or as a distance in the x-axis, horizontal distance, and the distance in the vertical component would just be the y values, well then I get my x and y's that I get to work with. Perfect. Now, let's go with this process. Again, we want to find out how fast this distance is changing. So we need some equation to now start modeling this. All right. So again, I don't want to put the cart before the horse. So I'm going to identify a few more items. Okay. This rate that was given to me, this 35 kilometers per hour, that was for ship A. I'm just going to call this, or I'm just going to say that this was a change in the x direction with respect to time, which was 35 kilometers per hour. But notice, from the initial point of observation, 35 kilometers per hour is approaching that point. It's not moving away. Therefore, this rate is going to be negative. Because again, it's approaching that point in question. So that distance is getting smaller. In other words, we're subtracting from that distance. The change in the y direction, change in y with respect to time, that rate is moving away from the point in question, which we're just going to denote as 25 kilometers per hour. Great. Let's go through the whole process now. If we have a distance d, then we know that the distance d is going to be governed by the distance equation. Or we can actually start looking at Pythagorean theorem here. Distance equation works just fine. However, if the distance equation that we're using has a centered, or has a, let's say positioned ordered pair for 0, 0, then that's going to be one of the pairs, and all we get is x squared plus y squared. So it's just a more compact way of that distance formula to work with. D squared is equal to x squared plus y squared. In other words, the Pythagorean theorem. And what I want to do here is I want to apply my derivative. And just as I'm saying this right now, I see that I have a d squared. And actually, I'm going to change that notation simply because when we take a derivative, we say d dt, and I don't want to take the derivative of the lowercase variable d in that instance. So I'm going to change that to a different variable. Let's just call this z. There we go. So now, when I apply the derivative with respect to time, and remember, you always want to apply the derivative with respect to time because we're assuming that my derivative, or that these functions, are functions with respect to time. Now, taking this derivative, we have to apply the chain rule. Well, applying the chain rule here for z squared with respect to time, we're going to go through and do the exponent. So 2z, so that's a power rule, multiplied by dz dt. Again, chain rule. Next one, again, taking the derivative of x squared with respect to t, we need to use the chain rule. 2x multiplied by dx dt plus, same process, 2y multiplied by dy dt. Perfect. If you notice all these equations now, all of these terms have a factor of 2. So I'm going to divide out by 2. Not only that, what I'm asking for, or what the question is asking for, is how fast is the distance between the ships changing? The distance between the ships is going to be this distance z. We want to know what is the change in that distance with respect to time. So when we solve for the change in the distance with respect to time, then we get x multiplied by dx dt plus y multiplied by dy dt, all divided by z. All we have to do now is evaluate these variables. So let's see. dz dt, and we're going to evaluate this at 4 p.m. So our time is going to be 4 p.m. Well, let's see. What's the x component at 4 p.m.? Well, the x component is 10 kilometers. Great. What's the change in the x component with respect to time? In other words, what's the rate of ship A? Well, since that distance is shrinking, that's negative 35 kilometers per hour plus y. So y, that y component is that 100 kilometers that we found, and that's at 4 p.m. The rate of the change for ship B is 25 kilometers per hour. All of this is going to be divided. Oops. All of this is divided by z. Well, z is the distance at 4 p.m. So we now need to figure out what is that distance at 4 p.m. because we don't have that. In order to figure out the distance at 4 p.m., we're going to have to go ahead and use Pythagorean theorem here. So the distance at 4 p.m., let's go ahead and let's write that out. That's going to be z is equal to, and I'm working on the left-hand bottom side of your screen, so z is equal to the square root of 100 squared plus 10 squared. That looks kind of nice. I can factor out a 10 squared from both of them. And that means I'm going to be left with 10 multiplied by 10 squared plus 1, which means this is 10 times the square root of 101. Perfect. So that distance at 4 p.m. is 10 multiplied by the square root of 101. Awesome. And again, that distance is in kilometers. So now let's go through the whole process. Okay, I'm going to have 10 times negative 35, so that's going to be negative 350. 25, then I'm going to have 25 multiplied by 100. So 25 multiplied by 100, that's going to get me 2,500, and then we're going to subtract out that 350 to get us a total of negative 2,150 kilometers squared per hour, all divided by 10 root 101 kilometers. This will now get us an approximation. Divided by 10 square root of 101. So I get negative 21.4. One of the kilometers unit of measurement is going to cancel out, which means we're going to be left with negative 21.4 kilometers per hour. What does this mean? Well, this is a change in the distance with respect to time, and this is happening at 4 p.m. Okay, so let's go ahead and let's write that out in a complete sentence. So the distance, between the ships at 4 p.m. is changing at a rate of negative 21.4 kilometers per hour. And again, if you wanted to get a little bit more technical, you can say that the distance between them, or the rate of the distance between them, is decreasing, and that would be okay. So there we are. This is that example. And again, what we have to do is draw the picture. Once you draw the picture, familiarize yourself with the variables that you're assigning. Then go ahead and assign the variables this function with respect to time. Analyze what equation will govern these variables that you're assigning. Take the derivative with respect to time, and then start making the substitutions for the values that were given to you. And we're going to work on a next example. This next example says that a kite 100 feet above the ground moves horizontally at a speed of 8 feet per second. The question is, at what rate is the angle between the string and the horizontal decreasing when 200 feet of string has been let out? All right, so that's so that's the question that we have at hand. All right, so we're going to go ahead and we're going to draw a picture here then to start off. So a kite 100 feet above the ground. Okay, so we're flying a kite 100 feet above the ground, and this kite is going to move horizontally at a speed of 8 feet per second. Okay, so I'll come back to that. So far we're going to have a kite That's 100 feet above the ground. So this is the 100 feet. And it's going to be moving horizontally. Okay, so this kite is moving horizontally at a speed of 8 feet per second. Okay, so I'm not going to say that this is perfect conditions, because in order for a kite to fly, we need some wind. So we're going to need some wind blowing in some direction. There we go. And the kite, I'm going to say, is here. Okay, there we go. That's my version of a kite. All right, so we know that this kite is moving horizontally at a rate of 8 feet per second. Awesome. So again, the kite is 100 feet above the ground and it's moving horizontally 8 feet per second. We have an angle though. So at what rate is the angle between the string and the horizontal? Okay, so that's where I have to now pay attention. The string and the horizontal. So the string and the horizontal, that means the horizontal line that is made with this point on the string. So we have some angle theta. Okay, so we got to keep that in mind. Have some angle theta. We want to find how much that angle is changing. So if you can see from this picture, if we were to animate this, the vertical height wouldn't change, because the vertical height would just stay the same at 100 feet. That means we would have to give more string in order to keep that 100 feet, because this kite is heading in a horizontal direction. That means that this angle will be decreasing. So the angle theta is decreasing. Okay, so again, we have some more to work with here. Awesome so far. Now I'm going to project all of this onto this particular height. So again, I'm going to project this onto here, this 100 feet. And the reason I want to do this is because I now have this triangle that I'm working with. I have some x component, so I have some x component, I have some y component, and I also have some distance here. Okay, so that distance, we can just call it z once again. I don't want to call it the variable d, simply because when we take a derivative, the notation might get in the way. Okay. So, we're given a rate of change in the x direction. Got that. The y values are staying constant. That's interesting. So y values are staying constant, meaning the y value is not going to change. Okay, I still want to account for it just in case something, a different question arises. But for now, I'm going to account for it as well. And they're asking me, or they're asking us to find at what rate is the angle between the string and the horizontal decreasing. In other words, we must find some value or some connection between x, y, and this angle theta. Doesn't necessarily have to be z here, because z is that distance of the string. And we know we're going to have a distance of that string when it's 200 feet. Okay, so that will possibly come into play. Don't know yet. We'll see. Okay, so now we need to think of either a geometric or a trigonometric, let's say, relation that will correlate x, y, and theta. Ooh, x, y, and theta. All right, I heard something. I time traveled to your time, and I heard somebody say, well, what about tangent of theta. Isn't tangent of theta just y over x? In other words, opposite over adjacent, and you're right, it is. So what I want to use here is I actually want to use this to say that I have tangent of theta is equal to y over x. Nice. Okay, so there's a few things happening here. Okay, well, let's see before we carry on. We said y is fixed, so y is not going to change. So our equation looks like this. This looks promising. However, if I take a derivative, x is in the denominator. I don't like that because then I'm going to have to use some sort of power rule to take everything into consideration. Instead, how about we take the reciprocal of this equation? In other words, cotangent of theta is equal to x divided by 100 feet. If we apply the derivative at this point in time, with respect to time, then what's going to happen here is that we're going to get some really nice observations. Derivative of cotangent of theta with respect to time. Remember, any variable that we assign will have a function represented in terms of t. So cotangent, the derivative of cotangent is negative cosecant squared theta. However, this needs to be accounted for with the chain rule, meaning that we now need to take the derivative of the inside, the derivative of theta, with respect to time. On the right-hand side, well, let's go through that process. We're going to get 1 over 100. So this is 1 over 100 feet multiplied. We're going to multiply by the derivative of x with respect to t. Okay. That's looking pretty good here. Now, remember, we got to keep the eye on the prize. The eye on the prize, this says that we need to find at what rate the angle between the string and the horizontal is decreasing. So we know the rate is going to be decreasing. That's fine. We're looking for a negative value, and guess what? We just see a negative value here, so that's promising when the string has been let out 200 feet. Okay. So what I want to do is I want to find the rate of change of theta with respect to time. In other words, I need to divide by cosecant squared, or negative cosecant squared. So let's divide. We're going to have 1 over 100 feet multiplied by dx dt, multiplying by 1 over negative 1 over cosecant squared theta is the same thing as dividing by it. Good so far. Let's bring this all the way to the top. Then we have the change in the angle with respect to time is still this 100 feet multiplied by dx dt multiplied negative 1 over cosecant squared. We can actually move this a little bit over. Let's move the negative to the very first factor. So negative 1 over 100 feet. Cosecant squared theta, that's the reciprocal of sine squared theta. So here we're going to multiply it by sine squared theta. That looks great. Now, the big question here is, do we know the change in x with respect to time? That, in fact, we do. That horizontal change was given to us by 8 feet per second. Ooh, that is awesome. I like that so far. Great, great, great. Now what I want to do is I kind of want to find out what this sine squared of theta is, because I don't know what sine squared theta is yet, but I want to find out. So what I'm going to do is I'm actually going to go to my triangle and I'm going to take a look at that, because there's one aspect that we haven't seen so far, and that one item that we haven't seen so far is this 200 feet. What in the heck is that 200 feet doing here if we're not using it? Well, let's take a look at sine. So sine of theta, according to my triangle, sine of theta is going to be opposite over adjacent. That's y over z. Which means y is a constant of 100 feet. Z, we're actually letting it out 200 feet. In other words, sine of theta is 1/2. And again, we don't need to know what theta is. That is great. So at this point in time, we now have -1 over 100 feet multiplied by the change in x with respect to time. We said that was 8 feet per second, multiplied by sine squared theta. Well, sine of theta is 1/2, so I'm just going to square that. There we are. And now we get to do some math. All right, so that's going to be -8. We have feet here, and we have feet in the denominator. Therefore, the feet are going to cancel. All right, that's nice. So in the numerator, we kind of left as unitless. There is a unit that is unitless, which sounds kind of weird. That unitless measurement is radians. So we get -8 divided by, that's going to be 2 squared, so it's going to be 4, so that's going to be 400. So we get -8 divided by 400, and this is a change in theta with respect to time. We can simplify this a little bit more. I get 1 over 50, and this is going to be radians per second. Is it decreasing? It sure is. I see a negative there. Are we talking about the angle theta? Yes, it is, because it's radians, time, seconds. Okay, I think we got everything then. Let's go ahead and let's verbalize this now. So the angle is decreasing at a rate of -1 over 50, and I can get a decimal here, so -0.02 radians per second when 200 feet of string has been let out. And there is our answer. So the angle is decreasing at a rate of -0.02 radians per second when 200 feet of string has been let out. That looks amazing. Awesome. So again, we're still working with the exact same process. We're still doing everything that we were initially doing. Again, we just keep on elaborating and finding new ways to relate all of these variables that we're doing or that we're working with. And again, you always want to start off with a picture. Doesn't matter how artistic you are. Look at my art. Man, you wouldn't even be able to tell that I was an art major back in school. Ha, that was a joke. Sorry. Please don't feel obligated to laugh at my lame jokes. So, next question. A paper cup has the shape of a cone with height 10 centimeters and a radius 3 centimeters at the top. I'm sorry, I was still thinking about that other joke. All right. If water is poured into the cup at a rate of 2 cubic centimeters per second, how fast is the water level rising when the water is 5 centimeters deep? Ooh, okay. So, what I kind of like to think of here, when I was a kid, we always went to the LA County Fair, and the LA County Fair always had the Sparklets, the Sparklets water there, and they always gave out samples of water as you were walking through, but they never gave you bottles of water or anything like that. They gave you these paper cups that were in the shape of a cone, and that's what you had to take the water from. So these paper cups that we were looking at, or that we were using, look like this. And so then the water was filled in as such, and we have a certain amount of water. There we are. And so that's what I always remember. Sparklets. I think it's 2 T's. There we go. All right, but this isn't an advertisement for Sparklets, so I will erase that. There we are. All right. Here we go. It'd be nice if they could sponsor me. Oh man, that'd be so cool. I'd rock a Sparklets t-shirt. Why not? So, here we go. So what I want to do is I want to figure out what I'm looking at. So, now that we have this picture for Sparklets at this cup, and it's a cone shape, we're going to extract everything that we know. So a paper cup has the shape of a cone with height 10 centimeters. Okay, so that 10 centimeters definitely not changing. So we know that if we were to identify some sort of center here to identify its height, that height would be 10 centimeters. The radius at the top, meaning at the opening, is 3 centimeters. Okay, so we have a radius of 3 centimeters. There we are. If the water is poured into a cup, so again, the water is now being poured into the cup here, and that water is going to have a rate of 2 cubic centimeters per second. So how fast is the water level rising when the water is 5 centimeters deep? Okay, so I can see here that what is given to me, the rate of the water going in, that's a volume per second. In other words, what they're giving me here, this rate of change, is the change in volume with respect to time. And I think that's the only thing that they're really giving me, the only rate of change. And that's going to be fine for what we have. So, what I'm going to do here now is I'm going to start identifying that how fast is the water level rising when the water is 5 centimeters deep. Okay, so I need to know that the water is going to be 5 centimeters deep, so that's measured from the bottom to the top. When we have 5 centimeters, so approximately exactly halfway through this cup, how fast is the water level rising? So that's the big key here. How fast is the water level rising? That is the key. What this is going to tell me, or what I'm going to extract from this is going to tell me that I'm looking to find some change in height with respect to time. Okay, so that's kind of what I have to keep in my mind. Now what I'm going to do is I'm going to start viewing some cross sections here. So let's start off by trying to view some of those cross sections. Alright, I did draw this just a little while ago, so I'm going to draw it again. So we have some height. We don't know what the height is, but we know we're going to have some height. So my height, I'm just going to denote as h. Notice that if you have some height that is not 10 centimeters, then your radius is also not going to be 3 centimeters. Instead, it's going to be a smaller radius. So that smaller radius is what we then need to account for, and we're just going to call this x. And what you're going to see here is that I'm now going to extract this triangle that I've made here with the initial radius of the opening of the cup, the height of the cup, this one of the sides, or a side for this cross section of the cup. So I'm going to extract all of this. There we go. So again, my opening was 3 centimeters. My initial height was this 10 centimeters. The height that I'm measuring is height h, so this is height h. You know what, let's make this a little bit better because I don't like the way that looks. So I don't guarantee it. That was a Men's Warehouse joke. You're going to like the way you look, I guarantee it. Okay, so we have some height h, and we're also going to have some other radius, which we'll call x. Now, you're going to notice here that we have two right triangles that share the same angle. We'll call this angle theta. It doesn't matter what it is because we're not using theta. So two triangles that use the same angle theta both have right angles, which means the final angle must be the same angle, which means these are similar triangles. Because these are similar triangles, we can now use geometry to relate these sides to one another. So we can say that 3 centimeters over 10 centimeters, so 3 centimeters over 10 centimeters is the exact same ratio as x, the side of x, over the side of h. And the big question is, why do I want to do this? Why? Well, the reason I want to do this is because when I'm going to be analyzing how fast this water is changing, how fast this water level is rising, I need to account for different variables. If I don't have information for those variables, I must find a way to make an equation that only contains one of the variables or only contains the variables that I've defined. So now that I have this, I'm going to come back to that in just a little bit because I don't know whether I want to solve for x and h. Well, I really do know what I want to solve for. I just haven't gotten there yet. All right, we don't want to cross that bridge yet. So how fast is the water level rising? Well, at first, or what we also need is we need to find a relation or this equation that will relate everything together. We have a change in volume, so we know the equation needs to involve some type of volume. We have a height and we have a radius. Oh hey, light bulb. What happens if we use volume of a cone? Well, the volume of a cone is 1/3 pi r squared multiplied by h. Awesome, right there. So if we take a derivative with respect to time, we know our radius is going to change and we know our height is going to change. And that height changing with respect to time is actually what we're looking for. So that's really great. However, we have to account for the radius changing. And if we don't know how the radius is changing or at what rate the radius is changing, it's going to be kind of difficult to extract. The workaround is to replace that radius, that amount that it's changing, with a different relation. Meaning, if we can make some connection between the height and the radius that will be connected proportionally, then we'd have it. In other words, can we solve for x? Si se puede. So we're going to solve. X is equal to 3 divided by 100, or sorry, 3 divided by 10, I don't know where I got 100 from, multiplied by h. There we are. Now we have this particular equation that will allow us to bypass this radius argument in the volume equation. So the volume equation, as we have set up, 1/3 pi, our r that's going to be changing is going to be x. So here we have x squared multiplied by h, which is the height. But we know that x can be expressed in terms of h. It's proportionally equal to it, which means x is equal to 3/10 h. So when we have our volume can be expressed solely on the variable h, or solely on its height. Let's simplify this before we carry on. 3 squared, that's going to be 9. 9 divided by 3, that's going to be 3. So this is going to be 3. 10 squared, that's 100. I have a pi. I wish I had some pumpkin pie, but hey. 'Tis the season. Pumpkin pie season. God, I love pumpkin pie. Alright, so volume is equal to 3 pi divided by 100 multiplied by h cubed. There we go. So now when we apply this derivative with respect to time, we only have to account for one variable changing, which is good. So on the left-hand side here, we're left with the change in the volume with respect to time is equal to the right-hand side, 3 pi divided by 100. That's a constant. So that just moves its way through the derivative. However, we need to take the derivative of h with respect to t, meaning we need the power and the chain rule. Drop the exponent forward. So this is going to be 3h squared multiplied by the derivative of the inside. That's the derivative of h with respect to t. Remember what we're finding. We're finding, or we're solving, for the change in height with respect to t. And I want you to pause for a second. Not pause the video, but just pause and observe. Do we know the change in volume with respect to time? Yes, that's given to us. Do we know the height? Yes, that is given to us. The height at a certain spot. That means we can solve for the change in height with respect to time. So let's start working with that. And again, I'm going to simplify this just a little bit more. That way I can keep solving for dh dt. Oops. I don't want red. There we go. So dv dt is equal to 9 pi over 100 multiplied by h squared multiplied by dh dt. And if I solve for dh dt, then I get the derivative of the height with respect to time is going to be equal to, and let's see, I'm going to divide by all of that. So this is going to be dv dt is going to be multiplied by 100 divided by 9 pi h squared. Let's make all our substitutions then. So the change in volume, we know that to be 2 cubic centimeters per second. We have 100 divided by 9 pi, and then we have our height that is given to us. that height that's given to us, we're going to say that this is at 5 centimeters for the height. So I'm really quickly going to rewrite this here and just say this is dh dt, and this is going to happen when h is 5 centimeters. Therefore, we have 5 centimeters here, and that 5 centimeters is going to be squared. Let's keep track of the units, and let's multiply everything. Alright, so in the numerator, I have centimeters cubed. In the denominator, I have centimeters squared, which means one of them is going to cancel, and it's going to leave with 1 centimeter, so or 1 of the centimeters. So 2 times 100, that's going to get us 200 centimeters, and I'll account for that in a bit. Denominator, well, the denominator, I have 9 times 25, which will get us 225. And again, the numerator, I had centimeter. The denominator, I still have seconds. And I still have a pi down at the bottom, but no pumpkin pie here just yet. Sad day. Okay, so now I'm going to go ahead and approximate this. Now that I have that exact answer, so I'm going to take 200 divided by 225 oops, I put 225 multiplied by pi. There we are. And I get an approximation of 0.283. Unit of measurement, centimeters per second. This is how fast the height is changing when the height of the water is 5 centimeters deep. So let's verbalize this. The water level is increasing at a rate of 0.283 centimeters per second when the water is 5 centimeters deep. And there we are. Boom. Nice, neat, concise. So again, draw your picture, extract what you have, take a derivative, find an equation that will correlate all of the variables that you've defined. Take a derivative with respect to time. Always take the derivative with respect to time. Once you have that, keep going. Substitute the variables that you know. At the end, you should be left with the rate that you are looking for. Last question. Save the best for last. We have here that a spotlight on the ground shines on a wall 12 meters away. If a man 2 meters tall walks from the spotlight towards the building at a speed of 1.6 meters per second, how fast is the length of his shadow on the building decreasing when he is 4 meters from the building? Ooh, that is a doozy of a question. I like that. So let's go ahead and let's start tackling it. All right, and the first thing we want to do is we want to draw that picture. So again, we have a spotlight on the ground. All right, so there's my spotlight. And it's shining on a wall that's 12 meters away. Okay, so here's my wall. There it is. Okay, so it's shining on that wall 12 meters away. So let's go ahead and let's identify that it's 12 meters away. Boom. So there we are, 12 meters away. All right. So a spotlight on the ground shines on a wall 12 meters away. Now we're introducing here a man that is 2 meters tall, and he's walking from the spotlight toward the building. So there's this person. All right, so here's this person. All right, there you go. That's my artistic value there. And he's walking towards the building. Okay, so I have him looking in the opposite direction, so poo on him. So he's walking towards the wall at a rate of 1.6 meters per second. Okay, so I got that so far. How fast is the length of his shadow on the building decreasing when he is 4 meters from the building? All right, so because we have some light here that is being shined. Let's see. There we are. So this light is going to cheese and crackers. There we go. So what I'm looking at here is that I have this light and it's shining on the wall. There we are. And so this person this man, he's walking from the spotlight toward the building. And so what we want to know is at what rate or how fast is the length of his shadow. So the length of his shadow on this wall, how much is that decreasing when he is 4 meters from the building? All right, so when he gets to about 4 meters from the building, how much is that going to be decreasing? And that's what we want to know. All right, so we're going to go through some problems here and we're going to figure this out. All right, how do we want to define x? How do we want to define anything else? So what I want to do first then is I want to try to identify that this wall has a certain length, all right, or let's say the shadow has a certain length. So that's going to be one of the first things that I identify, is that this shadow length, I'm going to say, has a certain height or length, whatever it is that you want to call it. All right, so let's call this H. H for height. Okay, so got some height there, perfect. And we know that the spotlight is 12 meters away. Great. Now, as this person is moving closer and closer and closer, this shadow is going to get smaller and smaller and smaller and smaller till it's the exact same height as he is. Well, as this happens, he's going to be approaching the wall, and what we want to do is we want to stop him, or we want to observe how fast the length of his shadow is then decreasing when he's 4 meters from the building. So we want to make sure we stop him when he's 4 meters from that building. Okay, so I'm going to take the same snapshot here. Here we are. Let's copy that. Look at that. Oh my goodness. Copy and paste on this technology is amazing. Okay. I'm just going to modify this a little bit, so try not to freak out too much. Okay, so Again, we're going to stop him when he's 4 meters from the building. All right, so now he's 4 meters from the building. Notice that his shadow now got smaller. Okay. Here we are. So again, his shadow now got smaller here. And again, we want to make sure that we account for that. So again, we stopped him once we got to that specific point. And so what I want to do is then I want to identify that we do have these certain spots that we're stopping this man at. So let's try to identify. We have a height, and now I want some sort of X value. You can measure the X value either from the wall to the person or from the spotlight to the person. However you want to measure that is perfectly fine. You should be able to get the exact same answer. I want to label my my variable X here. This is going to be measured from the spotlight to the man. Awesome. So in this particular instance, when the man is 4 meters from the wall, my X value is still measured from the spotlight to that man, which means this other piece is just 12 minus the 4 meters, which is 8 meters. I want to keep that in mind. Now, check out what's happening here. The man, he is 2 meters tall. We were given that. Look at this triangle here. I'll extract this just a little bit more. So we have H, we have 12 meters. Then we have the height of 2 meters. And we have an X value. Again, we have this proportion. The proportion then states that we can have H divided by 12 meters. So that proportion holds. H over 12 meters is the exact same thing as 2 meters over X. Again, we want to find out how fast this height is changing, or how fast the length of his shadow is changing, which means I got to solve for H. So let's go through and let's solve for H. H is going to be 24 divided by X. Looking good. Now we take derivatives. So let's apply the derivative here. Derivative with respect to time, apply it to that height. Derivative with respect to time, apply it to 24 divided by X. This piece here, well, this is then going to be the change in height with respect to time. This derivative, we can rewrite it as 24 multiplied by X to the power of -1. And we'll be able to see here that we have 24. Let's drop this exponent, negative X to the power of -2, multiplied by the derivative of the inside, which is just dx dt. In other words, we have 24 multiplied by dx dt, multiplied by dx dt, all divided by -x squared. And here's where the whole process now comes into play of what it is that we're observing. So again, we want to find out how fast that shadow is changing, and that's going to be finding what dH dt is. Now, I need to know what is the rate of this person, of this man, as he's approaching the wall. Well, that rate is then going to be 1.6 meters per second. So the derivative, or the rate of change of that shadow's length with respect to time when the man is 4 meters away, so I'm going to say at 4 meters away, this is going to be 24 multiplied by the rate of 1.6 meters per second divided by the x squared quantity. Well, x we defined to be the distance from the spotlight to the man. According to our view here, the distance from the spotlight to the man when he's 4 meters away from the wall is 8 meters. So this is going to be negative 8 meters squared. All right. And again, the unit of measurement for that 24, my apologies, but that unit of measurement for the 24 should be 24 square meters. And so now all we do is multiply. So we're going to take 24 multiplied by 1.6, and then we're going to divide it by negative 8. Oh, sorry, negative 8 squared. And I get, let's see, the unit of measurements for the meter squared, they're going to cancel, and we're going to be left with the unit of measurement of meters per second, and that's going to be negative, so this is going to be negative 0.6 meters per second. Makes sense because the shadow should be decreasing. So, let's verbalize this. The man's shadow is decreasing at a rate of negative 0.6 meters per second when he is 4 meters away from the wall. And that is all she wrote. That is beautiful. So I hope that you all enjoyed this lesson on related rates, and I hope to see you all for the next lesson when we're going to be talking about linear approximations and differentials. I will see you all next time.